Yeah. Well, well, okay. So oxidation numbers. All right, you notice I made a few changes on here because I noticed that I had those phases wrong last time. Take a look at bromine and iodine. They're halogens, but you notice that the common form of bromine is a liquid and iodine is a solid. So again, if you see bromine gas in any equation, its charge is not going to be zero. Okay. Your common elemental form of bromine will be the liquid. Yeah, bromine gas is going to throw all kinds of things in there, like increased enthalpy, all that fun stuff. Okay. Now, do we remember our rules for oxidation numbers? Oxygens are -2, hydrogens are +1. If you don't have any of those, you can start with an atom that is in a group on the periodic table that has a common charge. Let's see. Fluorine's almost always a -1. Halogen's almost always a -1. Sodium almost always a +1, stuff like that. Then you want the sum of all of your charges to equal the overall charge of your ion or molecule. Now, how do you know if your molecule or ion if your molecule has a charge on it? Nope. Upper right corner. If there's no charge there, it's neutral. So that'll be a charge of 0. Okay, so some of these are easy. Ag, what element is that? Nope. Silver. I always ask that because it takes a while to not get them backwards in your head. Au is gold, Ag is silver. Solid silver, what's its charge? That is a standard elemental form of a metal. H2 gas, standard elemental form, 0. But most of the time, silver goes to a +2. No, +1. Yeah, +1. Okay. Hydrogen sulfide gas. What do we want to, well, we want to start with the hydrogen, each one of them. And I'll show you how I do this, okay? Each hydrogen is a +1. I have 2 hydrogens, so I have an overall charge of +2 from the hydrogens. I do this so that at the end, when I'm adding things together, I can just add the numbers across the bottom and see if I get the right charge. So that's a neutral compound, so what does sulfur have to be? -2. Silver sulfide. Where do we want to start with that one? You want to start with the metal or the sulfur that is in the P block? By the way, where's the P block? Actually, it's on the other side of the B block. You have S block, D block, P block. Mm-hmm. Yep. And it's in a column, which it's in the same column as oxygen, giving it a common charge of, yep, -2. So whatever silver is, since that's a neutral compound, 2 of them has to add to a +2, which makes silver a what? Nope. Yep. +1. So your top numbers here, these are your oxidation numbers per atom. Your bottom numbers are total charges. Okay, now, which atom was oxidized? Yep, why? Well, it became more positive. So it lost electrons. So which atom was reduced? Hydrogen went from a +1 to a 0. Now, here's the fun thing. Well, actually, I'll write these in the reverse order so you can get it in your head. The reducing agent has the atom in it that was oxidized because it is the compound that's giving away electrons to another element. What was the reducing agent? Nope. It has the element in it that was oxidized. So in this case, it's just the silver metal. Because that silver, when it's oxidized, it gives off electrons to the hydrogen. And the same thing here, the oxidizing agent has the element in it that was reduced because it's taking electrons. Yes, but the entire compound. Yep, hydrogen sulfide gas. So when you're looking at the agents, you want the whole molecule. So that's not too bad. Now keep in mind, redox was from chapter 4, but you guys told me you didn't really cover it in depth. So we're going back to make sure we do, because again, those of you who go into microbiology are going to want to know oxidative cycles in both acids and bases. It's something you can get down real fast, but you need to know what it is. Okay. Simple redox balancing. And all of these, I've given you lists of rules, okay, or lists of steps. Until you get used to them, I would try to follow the steps. So the first thing you want to do is assign oxidation numbers, then separate into half reactions based off redox atoms. Find the number of electrons needed for each half reaction. You're going to add them to the more positive side because you're going to add electrons until both your sides have the same charge. Balance the electrons or scale them by using multiplication factors to make sure your half reactions have the same number of electrons. Then you're going to add the chemical equations together and cancel like species on each side of the arrow sign. Okay, real basic we're going to start with. First thing we want to do is assign oxidation numbers. Now you notice what phase are my ions in? Aqueous. Do my ions have to be suspended in aqueous phase? Yes. Otherwise, they are going to react with something. They're going to annihilate something else. They need to have some kind of suspension to keep them in ionic form. Also keep in mind, in acidic solutions and even in this balancing, we're going to use a symbol where we put H with a plus on it. Okay? Does the hydrogen ion exist in nature? It might exist there, but it's supported by something. Just in solution, does the hydrogen ion exist? No. What does it actually exist as in solution? It collides with water, forming you have H2O plus a positive hydrogen. You get an ion. Do you remember its formula? It's called hydronium, H3O plus. That's how it exists in nature. Why does it not exist as H plus in nature? This one's the cool part. A bit. Let's just say if you could actually get it to exist in nature, which I know how to, you have to have permission from the US government in order to do it. What does it become once you strip the electron off the hydrogen? Proton. It becomes nucleonic radiation. So it's not going to be exactly stable in nature, because if you just have random protons floating around, they are going to annihilate the living hell out of something. So in solution, it's going to exist as a hydronium ion. You're not really going to get those naked protons. And like I said, you usually have to get permission from some kind of government in order to have particulate radiation in your laboratory. Although it's not the bad radiation like Chernobyl, that's neutronic and gamma rays. You know, gamma rays only liquefy your organics, but that's another story. He's like, what's happening to my liver? Oh, it's a liquid now. So fun stuff. For protons, not really, no. Because when you're dealing with a proton stream, you're really just dealing with a very large electrical pulse. But still, it is a particle beam. It is nucleonic radiation. So somebody has to know about it. You can't just build a cyclotron. Somebody has to know. There's a famous physicist, Michio Kaku. When he was 17, he asked his parents, he goes, hey, can I build a Betatron in the garage? And they went, sure, that sounds awesome and intelligent. He built it, he turned it on, he blew out every single transformer on his street. I mean, he blew them up, just kaboom. So yeah, there are rules now. It's like, cannot build a particle accelerator without some kind of official knowing it. So now we're going to start balancing this. So we want to split this into half reactions based off redox atoms. So of course, one of those splits is going to be copper. The copper 1 ion becomes solid copper. And then your solid iron is split apart into iron 3 ions. Oopsie, I put the wrong phase over here. Oh, and always keep that in mind. If I write something down that seems like I've done some magic, I didn't. I just missed something, so please raise your hand. If we have time, I'll tell you where the phrase hocus pocus came from, because they don't teach you that in high school history. Hint, it comes from the Latin mass. There's a whole fun thing that people misheard the Latin, but the priest said something else, and it just entered the lexicon of pop culture. So we've now split this into half reactions. Now we want to use electrons to balance charges. The copper equation, how many electrons do I need and where does it go? Yep, to make everything neutral. Now, you can keep track of phases. Like if you're working on these, you can keep track of phases at every step. You also don't have to, just as long as when you finish, everything's in the right phase. So if you trust yourself to get the right phases on things, you don't have to keep track of them the whole way, okay? So, plus an electron gives us neutral copper. What about this? What about the iron equation? Yep. Okay. Now we need to scale these so they have the same number of electrons. How are we going to do that? Mm-hmm. So that's going to give us 3 copper 1s, 3 electrons, 3 coppers. Now I'm going to add them together. And when you add chemical equations, what you're going to do is take everything on the left, bring it all down, take everything on the right, bring it all down, and then we're going to cancel out anything that's the same. And the only thing that's the same is the 3 electrons, those go. And our balance, oopsies. Again, make sure when you finish, you have the right phases on things. Now, at first glance, this might seem pretty straightforward, but if you didn't have your steps and you just went for that very first equation, could you have figured out how to get to this balance? Because what are the 3 things that have to balance in a redox equation? And you've been balancing atoms already. That still has to balance. Electrons have to balance. What else? Overall charge. Atoms, electrons, charge, all have to balance in a redox reaction. So again, here, you notice +3, +3, the charges are also balanced. Okay, now that we've warmed up with the easy one, you're going to do something that will enter your nightmares, but it's something you need to see so you can do it next year. Also, I pulled these from the end of your chapter 4 in your textbook. So these are problems in your textbook. So, okay. Balancing redox in acidic solution. So again, assign oxidation numbers, separate into half reactions based off the redox, balance every other element other than oxygen and hydrogen, okay? Then you're going to balance your oxygens with water. Then you're going to have an excess of hydrogens due to the waters that you put in there, so you're going to need to balance with protons. Balance hydrogens with protons. Then you're going to balance the charges with electrons. Then you're going to scale the half reactions to make sure they all have the same number of electrons. Then you're going to add everything together and cancel like terms, okay? So, let's do this one. Oh, here's a fun little piece of trivia for you biology people. You know how every group of animals has a name, like a murder of crows, a gaggle of geese? Do you know what a group of pugs is called? It's called a grumble. That's the best name for a group of animals ever. That, and not too long ago, around 2010, there was a new species of bee discovered, and the scientists couldn't figure out what to name it, so they can't use the Latin phrase that translates into cute bee furry face. You can look that up on Google. So they just Latinized cute bee furry face. Bismuth. So we have a manganese 2 ion. We have a bismuth ion. So let's look at these others. Okay, let's look at this sodium bismuth O3. Let's do that one. So let's start with oxygen. Each oxygen is a -2. 3 of them gives an overall charge of a -6. Which element do I want to do next? Bismuth is a metal. Sodium comes from group 1. So do we want to, which one do we want to do? Sodium, because group 1 has a common charge of +1. Now, I have a neutral compound. I have a +1 and a -6, so the bismuth has to be what? +5. Let's look at MnO4-. What's the name of that? It's one of your oxoanion families. MnO4. That is the permanganate ion. Yep. So each oxygen is a -2. 4 of them in total gives a -8. What does manganese have to be to maintain the overall -1 charge? +7. So now you'll notice that bismuth is reduced and manganese is oxidized. So that's going to be our half reaction split. Okay. All righty. All right. So that's our split. Now balance every other atom other than oxygen or hydrogen. How am I going to do that? Balance every atom other than oxygen or hydrogen. Well, I have one manganese. That's done. What's wrong with the second one? We'll get to oxygen. Everything but oxygen and hydrogen. There's no sodium. So how do I want to balance that? Yep. Sodium ion. Okay. Now I'm going to balance all of my oxygens with waters. So in the manganese equation, do you notice I have 4 oxygens on the right side? That means I'm going to need 4 waters. I'm going to go ahead and put the phase in here and we'll talk about it. We'll need 4 waters to balance those 4 oxygens. Make sense? So, and please put liquid as the phase for water. There is one situation, and you will learn about it this semester, where water aqueous makes sense. But if you put aqueous, I'm going to make you come up in front of the room and explain to everybody that one situation. Because otherwise, what you just told me is the water is dissolved in water, man. It's like, no kidding. Thank you for that. That's great. So let's make sure we do water liquid. And the one time that it makes sense is called autoionization. The water reacts with the water to form ions. So in that case, water molecules were dissolved and water molecules become ions. It's a whole process. Now, for the sodium and bismuth equation, I have 3 oxygens on the left. I need 3 waters on the right. Okay, so I've done that. Now I need to balance all of the hydrogens using protons. For your manganese equation, what am I going to do? Yep. Because that will take care of, that's 8 hydrogens on each side. So for the bismuth equation, I'm going to need 6 hydrogens or 6 protons on the left. Okay. Now I need to add electrons to balance the charges on each one. So let's take a look. In your manganese equation, this whole side is a +2. This whole side is a +7. Do you see that? You have 8 protons and a -1 charge, so it's a +7. How many electrons am I going to use and where are they going to go? You put electrons where it's more positive to make the charges balance. How many more? 5. 5 electrons. Now both sides are at a +2. What about the second equation? I have a +6 on this side. And +4 on that side. How do I balance those? Yep. Okay. Now I need to scale everything so you have the same number of electrons in each equation. How am I going to do that? Mm-hmm. Yep, lowest common multiple. You have to meet at 10 electrons. Okay, so I'm going to go ahead and put these in a format where I can just then add them. Okay, so water. Two manganese ions. Two permanganates. 16 protons. 10 electrons. And then we're going to have 5, the sodium bismuth molecule. Plus 30 protons. 10 electrons. And yes, sometimes numbers can get big in these. Don't let that bother you. I have the bismuth ion. 5 sodiums. 15 waters. Now what I'm going to do is go ahead and add everything together. It's going to be a big one. Now, I add everything together, then cancel. If right now you decide to cancel the 10 electrons, I don't care. All righty. So let's cancel terms that are the same. 10 electrons is the same on both sides of the equation. What else is the same? Well, look here, I can cancel 16 protons and reduce this to 30 to 14. There's one more I can do. Which one is it? Water. I can cancel 8 of the waters and reduce the 15 to 7. You see that? And so what I have left remember how I told you at the end, you have to make sure your phases are correct. So you can either keep track of them the whole time or put them back in at the end, but make sure they end up there and they're correct. Yeah, I know. I made it up to torment you. What else are Mondays for? No, what you're taking account of here is not only do you have a redox reaction occurring, but it's occurring in a solution where you have excess positive charge. So it is in an acidic solution. So in that solution, there's going to be water, there's going to be hydronium floating around. And so all of that's going to play into the chemical reaction. And so the acidic solution can facilitate the redox, but you have to take into account everything that's involved. So this is our balance of a redox reaction in acidic solution. And again, you have to balance atoms, charges, and electrons. Okay. You're going to work together in groups for a few minutes, work on another one. Not quite as in-depth as this one, but it has a little trick all its own. You're going to want to do something that you're not supposed to do. So we'll see who falls for it. Do you have everything? Are you okay? You look a little traumatized. It's okay. Just engage the system. You'll do fine this semester. No, we should try quantum mechanics. There were homeworks I turned in where one problem was like 10 to 12 pages. Just all the derivation and the differential equations. Oh yeah. Oh yeah. Okay, this one you're all going to work on together. We'll do this for a few minutes. You probably won't get done with it, but I just want to see how far you can get. CR2O7, you've seen that before. What is the name of that ion? Chromium is the metal in there. The orbital becomes the octahedron. So two chromiums. What kind of prefix is that? That? Dichromium. It's dichromium. Oh. This is the dichromium ion. This is another one that you will see on standardized examples. We're in lockdown mode. We're going in lockdown. Go get the Rice Krispie treats. We can survive. What I love is when I go to the things on campus for keeping students safe, and they say if you go into lockdown mode, bar the doors. They go, you mean the doors that open out? And then I had to explain to them. They're like, bar the doors. And when the police get there, they'll get in. I go, no, they won't. And he goes, the police can get in if they want to. I'm like, I'm a physicist. When I bar something, it's barred. And it would be frustrating for them because someone goes, it's the police, open the door. I don't believe you. But I have a badge that can say. I don't. Well, remember you thought in the money, that overall this. But make sure you have each time yes. Yes. This one is a standard element of right. Yeah, so that one. You really only have to take apart the dichromium. Did anyone make it to the one class session you had last week? Okay, so there was a problem that a lot of students were solving. Oh, did it? Well, no, it was one where it was like P1, V1 equals NR P1 divided by P2. Is that the way Sean showed you?
Yeah.
Okay, good. So, so maybe we'll make a rule that if he shows you something different than a process in the book, what we used in class, just write Sean said is this, okay? Because that process, it's a correct way to do it. I just didn't show you that in the book, didn't show you that, so where did it come from?
They saw like everything.
Yes. So I was like, this had, unless they were all using the same AI, this had to be. So that's what I figured. Because there were a couple of things, there were some grades that changed as time went along. Because like the first couple, I hadn't told you that at STP there were 22.4 liters of oxygen per mole. The people were using that. And I was like, where'd you get that from? But then I was like, oh, there's a table in the chapter that says that. So you'll see that as I'm grading, grades will change. You just take practice. I really like the students being on the line. Well, before I had a manual before about the trial. It's one of these things that says, if the earth was round, the bottom of your shoes would look like this. I'm like, yeah, if the earth had the diameter of a basketball. So I asked him, I said, when you look out at the horizon, and you see something flat, that is the differential of the curve. And they can tell me the differential of the curve is. And if no, then you shouldn't have it.
Yeah. Okay, so.
Well, can you tell me about how space-time geodesics will work when you're talking to the gravitation technology? No, it's round. But it's not a perfect sphere, do you know why? More than that, it's the magma underneath the crust. And when you take a liquid and you spin it, what happens to you? And it falls it. So I like that one the wide is further than the low side. Yep. Yep. Also, a place I want to visit is either the planetarium or the observatory in Hawaii or Chile. Because they're so high up on the mountains that they essentially eliminate all atmospheric disturbance in the telescope. You're supposed to have equal amounts on each side. So if you have 20 on one side, none on the other, yeah, try not to stress too much. It's going to be a challenging semester, but you'll do fine. You know, keep in mind, part of actually succeeding in science is having the will to hold on. Because you're going to see a lot of people, as soon as it gets hard, they're going to quit. Good. And we'll start those back up again at the end of this week since everyone has internet back. I just want to make sure things are stable before we start that again. I got a message that some people were on like a trial, like they hadn't paid for the sim gauge yet. So if you lose access, you were on a trial. Yeah. Yep. Mhm. Yeah, you need to be able to access the assignments and the questions.
I had a trial meeting. It's been like, it's Saturday, someone hacked, I got my cards up, sent them out. Or,
Oh my gosh.
like, I can't buy it. I don't know if I'm money.
That is, that's why if you're ever so inclined, a great career, make a lot of money, but you mess with people. It's called an ethical hacker.
Yeah,
You actually once you're that person, you have to register with the government because of the skills you have. But then your job is to like you get paid by corporations just to break their system. That or you also you I know people who work for the government and they take down the foreign scam artists, you know, okay, we're running out of time, so I'm gonna start going through this. So that's what your charges should look like. Okay, so those are our half reactions. Because you notice the chromium was reduced and the chlorine was oxidized. Okay, so let's make sure all of the atoms are balanced other than oxygen and hydrogen. So I need a 2 there and a 2 there. You see that? 2 chlorines, 2 chlorines, 2 chromiums, 2 chromiums. Okay, now let's balance the oxygens with water. And I do nothing at all to the chlorine equation. Now I'm going to balance hydrogens with protons. And I do nothing to the chlorine equation. This was the part I wanted to see if you would fall for. You're like, I have to do something to the equation. Why am I doing nothing to it? Well, there's nothing to be done yet. Now I'm going to balance charges with electrons. Okay, well, if I look, I have a plus 14 and a minus 2, so that's a plus 12. Then I have a plus 6 on this side, which means the left side is going to get 6 electrons. Okay, and so then I have a minus 2 and a 0, which means the left is going to get, or the right is going to get 2 electrons. Okay, now I have to scale these to make sure they have the same number of electrons. Well, that's easy because I can just multiply this one by 3 to get 6 electrons in both of them. Okay, so when I write these in order to add them together, and then I'm going to get 6 chlorides, 6 chlorines, and oh, not 6, 3. 3, 3, because it's 6 electrons. All right, so let's bring everything down. All righty, so 6 electrons goes, and that is the only thing I can cross out. The what? Nope. Because you go from ions to compound. Now, I haven't been tracking them, but I need to make sure that my phases get back in. And that's your balance. Ions are pretty easy. If you're ever wondering at your phase, go for aqueous. Water should be liquid. You might have to search for the chlorine to make sure you realize it's gas. And so when we come back on Wednesday, just because I thought it was funny, did everyone get this? Are you guys still writing? So I put these in because I thought they were hilarious. And then, but wait, there's more. So on Wednesday, we're going to then take this and look at redox in a basic solution. It's two more steps, but it's just using hydroxides. So you do everything like you did in the acidic one. No, you're still going to do that. You're going to add the protons, but then after you add everything together, you're going to see which side has the most number of protons. You're going to add that many hydroxides to each side. And then you're going to combine protons and hydroxides into water and then do some more canceling. Oh, okay. So